Hi guys, welcome to the playlist of advanced data structures. In this video, I'm going to start a new advanced data structure that is tries. So what all I'm going to cover in this video? First of all, I'll have to give you a brief background about string matching in order to explain you the importance of tries. And then I'll talk about what are tries. I'll also give you an example. Then we will talk about different operations on tries. Then we will see the time complexity of those operations. Then we will also find out the space complexity when we use tries. And then finally, I'm going to end this video by talking about the drawback of standard tries, right? So in this video, we are going to cover almost each and everything about this interesting data structure, tries. So let us briefly see what is pattern matching. So if you want, later on I'll cover pattern matching in detail, like different algorithms in pattern matching like Rabin-Karp, KMP algorithm, then string matching with finite automata and the naive algorithm. So we will cover all that in detail, but right now just let us look at that part in pattern matching which will be useful in order to learn this data structure that is tries, okay? So what do you do in pattern matching? Very simple. You have been given a text, let us call it T, right? And you have also been given a pattern, let us call it P, okay? So you have been given a text and a pattern. Both of these are strings. You are being asked that search for this pattern, that is ABC, in this text EBA, DABC. So we need to search that where does this pattern, on which positions does it occur in this text. So which is the most simplest method? What you can do? You can take this text, that is EBA, DABC, and then you can check each of the substrings in this text, right? Like first you will check if EBA is equal to this pattern, ABC, and then you will find out that it's not equal, right? Because these two are not equal. Then you will check the second substring starting from B. So you will check BAD, right? So this is the second substring starting from the index 1, right? You will check it again with your pattern ABC and you will find out, okay, it doesn't matches, right? Because BAD doesn't matches with ABC. In the same way, again, you will check ADA, right? So in this way, you will check all the substrings, right? And then finally, you will check this last substring, right? This is the last substring you need to check in your text T to look for the pattern P, right? And then you will check ABC, does it matches with the pattern? Pattern is ABC. Yes, it matches. So what you would do in this case, you return this index, right? Which is this index? This is 0, 1, 2, 3. You return the fourth index, that the pattern ABC is present in the text T at index 4. So this is the problem statement, right? In order to find out the position of pattern P in the text T, it is possible that this pattern might not be present in the text. Like if you change the text to this, in this case, this pattern is not present in the text, right? So according to you, what is the time complexity of this entire pattern matching that you are doing? So suppose if we consider the length of the text as n and the length of the pattern as m. So we are actually checking at each and every position, right? That the pattern is present or not. And we are checking until this position. We are not checking until the last position, right? So we are checking until the n minus m plus 1th position, right? This is the n minus m plus 1 position. And how many characters we are traversing in a single check? As you can see, we are traversing 3 characters. So these are the number of the characters that are present in your pattern. So for n minus m plus 1 positions, we are traversing those number of characters that are present in the pattern, right? So this will be equal to m. So your time complexity is equal to n minus m plus 1 into n. This can be, this you can call as n into m, right? So this is the naive algorithm that we use. But what I am doing over here is a very inefficient way of doing pattern matching. So many advanced algorithms are also present for this process, like Rabin-Karp and KMP algorithm, string matching with finite automata. So if you want me to make videos on that, please let me know in the comments. I'll do it later on. So now let us focus on this. So the time complexity we got was order of nm, right? So this time complexity by those advanced algorithms, if you use them, is actually further reduced to order of n, or the order of the length of our text, right? So n is the length of our text. So this time complexity, by using some of the advanced algorithms, it is reduced to this much, order of n, right? And how it is reduced? We actually perform some kind of pre-processing on this pattern. On this pattern P, we perform some kind of pre-processing steps. So suppose we find out the hash value of ABC as 5, right? Just suppose. It depends on the hash function. So we will store this hash value. This is our pre-processing step. And then we will compare the hash value of each and every of these strings with the hash value of ABC, right? And if this hash value matches, right? If this hash value of ABC matches with the hash value of this substring of our text, then only we will compare that substring of the text and the pattern. Otherwise, if the hash value doesn't match, we won't compare these substrings and this ABC. We won't do is E equal to A, is B equal to B, is A is equal to C. We won't do that, or we won't traverse this much length if we find out that the hash value is different. Because if the hash value is different, there is no chance that these two texts can be same, right? So we have to choose such a hash function. So this pre-processing we perform on the pattern, right? But even if we do that, the best time complexity that we can achieve is order of n. We achieve this time complexity using KMP algorithm. In that KMP algorithm also we perform a pre-processing step on our pattern P, right? So even after doing that, the time complexity that we get is of the order of the length of our text. So suppose your text is actually, rather than being a small string, it is actually of the length of 1 lakh words. Or you can consider your text is very large and it is also immutable. Like suppose that you can consider it as all those books that are written between the year 1950 and the year 2000, and your pattern is that you are searching for the word Hitler in all those books, right? So now you can understand that if you get the time complexity as the length of this entire thing is n, right? And the length of this entire thing is m. So if you get the time complexity as the order of n, just consider how much time will it take in order to perform this operation of pattern matching, right? So why this is happening? Because we are performing every time the pre-processing step on our pattern, right? We are finding out the hash function of pattern sometimes we are finding out the prefix array for the pattern in a different algorithm. So what we want is that this time complexity that we are getting of the order of the length of our entire text, which is actually too large, we want it to be of the order of the length of our pattern, that is order of m. Because we know that our pattern is going to be very small. So we want that our length of our pattern, which is actually very small, right? It is very small. It is just a small string. That should actually be our time complexity in order to perform pattern matching. So for that, what we need to do is that we need to perform the pre-processing step on this large text rather than performing it on our pattern on this word Hitler as we used to do earlier. Right? So if your time complexity is of the order of the length of your pattern, your operation will be performed very efficiently, right? The pattern matching can be performed very efficiently. But in order to do this, what we have to do is that in the first step, before performing pattern matching, we have to do the pre-processing not on our pattern, but on our text, right? But this is going to be a one-time operation. This pre-processing of text is going to be a one-time operation because our entire text of 10 million words is actually immutable. It is not going to change. So after that, when you do pattern matching on this large text, you don't have to perform this step again and again of the pre-processing of text. So whatever steps you performed over here, you can store them, and then later on, for each and every pattern matching, the time complexity that will come is that order of m. So this is the first pattern matching that you do with some pattern, then this one with some other pattern on this entire text. So in order to perform this pre-processing of our very large text, tries is the best data structure, right? So that is why we need tries. In order to perform pre-processing of text in our pattern matching. There are many other applications of tries that I'll discuss later on, but this is one of the reasons that why we need tries, right? Because it has actually reduced the time complexity of pattern matching from order of the length of our large text to the order of the length of our very small pattern, right? From order of n to order of m. Now I hope that you have understood that why do we need tries. Now it is time to ask ourselves, what are tries? So now let us see what are tries. So basically trie is an ordered tree to maintain a set of strings. So these are the two important things, ordered tree and set of strings. So I have drawn a trie over here, and as you can see, this is an ordered tree, right? Because here you can see first there is C and then D. Here also if you look at A, if you look at the children of A, they are arranged in alphabetical order or in an order. P, R, then T, right? Even in this case, first G, then O. So it is an ordered tree. And as you can see over here, it is not a binary tree, because in binary tree, at most there are 2 children, right? And it maintains a set of strings. So basically how I have drawn this trie, I have inserted all these strings, cat, cap, car, dog and door, in this data structure in order to form a trie, right? So it is a set of strings. This trie is actually maintaining all these strings. So this is basically my text that I was talking about earlier, which can be very large, right? Here I have only drawn a few words. It can go about 10 million words, right? This trie can also contain 10 million words. Suppose I also take a pattern, dog, dog, okay? So now how am I going to search this pattern in this text when it comes to tries? So in order to search this pattern dog in this trie, I'll always start from my root node, and I'll start from the first letter of my pattern. So the first letter is D. So I'll check if this root has any of its child as D. Yes, there is D over here. So I'll come over here. Then I'll go to the next letter of my pattern, that is O. Then I'll see if this node D has any of its child as O. Yes, it has a child O. So I'll come over here, right? Then I'll move to the next letter of my pattern, that is G. And I'll see if this O has any of its child as G. Yes, it does. So I'll come to G, right? And then I'll finally declare, because my string has ended or my pattern has ended, and I've finally found it. So this way I do string matching when it comes to tries. As you can notice over here, how much time did it take us? We actually visited how many nodes? We visited those many nodes that were equal to the length of our pattern, right? So here, as you can see, the time complexity for searching a pattern in a set of strings or in a large text is actually order of length of pattern, right? So the time complexity is the order of the length of pattern, and we said that earlier that the length of pattern is actually m, so it is order of m, right? So this is actually the time complexity. This is the advantage of tries, right? We can search in so much less time as compared to taking the time of the order of the length of our large text, which can go as large as up to 10 million words, right? If it is a very large text. So now we have understood this. So now let us understand the structure of each of these nodes, right? Because as you can see here, A has 3 children, O has 2 children, while R doesn't have any child. So how do we actually code the structure of a particular node? Let's dive deeper into that. So basically each and every node will be a structure. Let us call it trie node, okay? And as you can see, each and every node is having a character associated with it, right? So it will have to store a character. Let us call that character as data. And then apart from that, for each and every node, there are pointers to the children. So how many maximum number of pointers can be there? So basically maximum 26 pointers can be there, because this A can point to another A, B, C, D. In this way it can point to even Z, right? Because here we are only considering the lowercase letters. So here we are considering maximum 26 number of pointers that are coming out of a particular node to point at its children, right? So it will have an array of pointers, right? Each and every node will have an array of pointers. Apart from that, we also need to know that when a word is ending, right? For example, if over here in my text, I also want to insert do, the word do, right? So how I'll insert? So first of all, I'll come at the root. So I'll see if it is having a child D, as the first letter of do is D, so yes it has, then I'll see the second letter of do, so is this D having a child O? Yes it is having, so here my word is ending, so I want to store this word. But how will I represent this node as the end of the word do? Because many children are actually coming out of this O, right? So in order to store the end of a word, because here we want to show that the word do is ending, we actually store another integer word end, right? We can call it WE, right? So these three things actually represent the structure of a node, right? So each and every node can be represented in this way. So we will draw the same trie over here, but we will look at this structure when we draw that trie. And in that way, we will also learn the insert operation, right? So at the top, we will always have a root node. And this root node doesn't contain any character, as you can see over here, but it will also have 26 children like the other nodes. And so we will draw an array of pointers over here, right, of 26 children, starting from 0 until 25. And the word end value over here will be 0. So now suppose we want to insert the first word, that is cat, okay? So now if you want to insert cat, how we will insert cat? So we will check the first letter of cat, which is C. So one of the child of this root should be C, right? So which pointer we will use to point at C? So we will use the pointer at this index. This will actually come out to be as 2, right? So we will start a pointer at 2 that will point at C. So let me draw C. So the character value or the character data in this case will be C, right? And the word end value will be 0 because the cat word is actually not ending over here. And again we will have an array of pointers, right? Then the next letter in the word cat is A, right? So now this C has one child which is A. So we will draw A, and here we will store the data value A, and word end over here will also be 0 because the word cat is not ending at A, right? And then we will store T, right? So one pointer out of these 26 pointers, as over here A represents 0, B represents 1 and C represents 2. In the same way, whatever T will represent, that pointer will actually point at T, right? So we will draw a T over here. So here the word end value will be 1, right? Because the word cat is ending over here. So whenever we are inserting a word and at a particular node that word is ending, in that case we increment that node's word end value, or we increment WE. So in this case WE will be incremented by 1, right? So now here as our word has ended, so all these pointer values will be null, right? Okay, so here also rest of the pointer values will be null, right? And here also rest of the pointer values will be null. So now let us insert the next word, right? Now let us insert cap. So first we will start from the root. We will see if this root is pointing to a child C, which is the first letter of the word cap. Yes, it is pointing to C. So we will not create a new node. We will just come at C. And then we will check the next letter. So is this C pointing to A? Yes, it is pointing to A, right? So we don't create a new node. Then we look for the last letter. So is this A actually pointing to P? No, it is just pointing to T. So in that case, we should actually make the P pointer. So basically P will also correspond to a value, right? So the pointer on that index of that value on which P will correspond to, so will actually point at another node that we will create, that is, which has a character value as P, right? And here also the word end will be 1 because the word cap that we have just now inserted is ending over here, right? Here all the array pointers will be null because the word has ended, there are no more children over here. So in the same way, let me insert everything and show it to you. So now I have inserted all these 5 words and I have actually made the same trie that I made over here, right? So that you can understand the structure of a trie, right? So so each and every node follows this structure. So now let us see different operations on this trie. Let us perform the search operation for the word door, right? We will search for door first. So we will start from the root, and here we will start from the first position, right? So does this root have any child D? Yes, it does. So now we will move to the next position in this word that we are searching. Does this D have any child O? Yes, it does. So we will move to the next position in this word. So again it is O. So does this node O has any child O? Because the next letter is again O. Yes, it does. And does this node O has another child R? Yes, it does. So our search has ended at R, and here also it is representing, and here the word end value is actually 1. That means here a word is ending, right? So that means our search is successful. Now let us search for another node. Let us search for coat, C-O-A-T, coat. So we will start from the root, and the first letter is C. So does this root have any child C? Yes, it does. Then we will look at the next letter of this word, that is O. So does this C have any child O? No, it has only one child A. So that means this search was unsuccessful. So this was a successful search. This is an unsuccessful search in a trie, wherein the word that you are searching for is not present. So this was the search operation. So as you can see in the search operation, I just had to traverse the length of the word that I was searching for, right? So the order of the time complexity of search is again order of m, where m is the length of the word that I was searching for, right? So the order of the search operation is the order of the length of your pattern, right? So now let us see the delete operation. Let us delete the word dog. So in order to delete the word dog, first we need to search the word dog, right? So we will start from root, then we will go to D, then we will go to O, and then we will go to G, right? So we have found the word dog. Now, so when our search ends at G, so what we do is that we delete this node, right? We delete this node. And after that we move to its parent. And here we see that if this parent has got another child apart from this deleted child, then we will not delete this node. But if this parent would not have had this child that it has right now, in that case we would have deleted this parent O, right? So now we won't delete it, because if we delete this node O, that will also delete the word D-O-O-R, door, right? Because door was also inserted in our trie. So that we don't want. That is why we don't delete this node, we simply delete this node. So in this way we have deleted the word dog from our trie. Now let us just insert a word, cat, okay? Now you will say cat is already there, but there is no problem in inserting cat again. So we come at C, then we come at A, and then we come at T. Because at the node T, the word cat has ended, so we need to increment the word value. So it will change from 1 to 2. That means there are 2 words that are ending at this node T, right? So now as you know, there are actually 2 cat in my trie, right? Already there was a cat and now I have inserted another cat. Now suppose if I want to delete a cat, okay? If I want to delete a cat from this trie, okay? So what I have to do? So I'll first of all search for cat. I'll start from the root, then I'll go to the first letter, that is C, then I'll go to the second letter A, then I'll go to the third letter of cat, that is T. So the T is over here, right? Then what I'll do is that, because here my search of cat has ended, so now in order to delete this node, I have to decrement the value of word end. In case of insert, when we reach the last letter, we increment the value of word end. And in case of delete operation, when we reach the last letter of the word, we actually decrement the word end value of that node that represents the last letter of the word, right? So here the word end value will decrement by 1 and it will be 1 again, right? Now, as in this case, we deleted this node when we were deleting dog, we cannot delete this node. Why? Because here the word end value is still 1. What that implies? That implies that there is another word that is ending over here. So if we delete this node, that will also delete that another word, right? That is actually ending at this node. So in that case, we cannot simply delete this node, because that will delete another word that must be ending over here, because the word end value is still 1. So if our word end value is actually greater than or equal to 2, that means there are multiple words that are ending at this node, right? So in that case, we cannot delete the node. But if the word end value is less than 2, in that case, that means this node that we want to delete was the only word that was ending over here, which had incremented the default value of word end from 0 to 1. Let us delete the last node, that is door. Okay. Now let us delete door. So we search for door. So the first letter of door is D, so we come over here. The first letter of D, the second letter is O, so we come over here. The third letter of door is O, so we come over here. The fourth letter of door is R, so we come over here. Okay, we found door, and as you can see, the word door is ending over here, so its word end value is 1. But we can delete this node. Why? So we can simply delete this node, right? And then we come to its parent. We can also delete this node because here the word end value is 0. That means that there is no word that is ending over here, right? So we can also delete this node, right? So we have deleted these nodes. Now we come to the parent, right? Now we can now let us check if we can delete this node. We cannot delete this node. Why? Because the word end value over here is actually 1. What that implies? That implies that there is actually a word that is ending over here, right? And what is that word? That word is D-O, do. So the word do that we inserted earlier is actually ending at this position. So we cannot delete this node because that will also delete the word do. So we stop over here, right? So our delete operation of the word door is actually completed after we delete only these two nodes, and we will not delete the rest of the nodes, right? So this thing, what I told over here, is actually applicable on the last node, right? On the last node, or you can call it the last letter of the word that has to be deleted, right? And in the case when it is not a last letter, so in case of the else condition, you cannot delete a node if the word end value is actually greater than or equal to 1, not greater than or equal to 2. Even if it is greater than or equal to 1, that means there is a node ending at that place. So you cannot delete that node, as we did in this case. We did not delete this node, right? So this was the delete operation covering all its cases. So what is the time complexity of this delete operation? How many nodes you had to traverse in order to delete the word door? So you first of all traverse the length of the word. You traversed all the nodes D-O-O-R. Then in order to delete the nodes, in the worst case, you have to traverse back the entire length, right? Suppose we would have deleted these two nodes as well. So we would have to traverse back the entire length of this word again. So basically we are traversing this length twice. So our time complexity will be, you can say, order of 2 into the length of this word. If the length of this word is m, so order of 2 into m, that is order of m, right? So the time complexity for the delete operation is also very less. So if we consider the length of the word that we are deleting, inserting, or suppose searching, if we consider the length of that word as m, for all the operations the time complexity will be order of m, right? Now you might be thinking that you are able to perform these operations so efficiently because you are getting such a low time complexity. That means there is nothing wrong with this data structure trie. But the efficiency of any operation is not just determined by its time complexity. You also have to take into consideration the space complexity. And here, as you can see, if there are millions of words that are there in our text, right? In that case, we need to insert all those millions of words because, as I told earlier, we are doing the pre-processing, or we are storing the words of our text, not of our pattern that is as small as this. So the space complexity of this trie is actually very high. So suppose the length of all the words in your text. So earlier I talked about two things, that is text and pattern, right? And we took a condition where our text would be very large and it would be immutable, right? So we saw over there that the length of the text will be n, right? And the length of the pattern we saw was m, right? So when I say the length of the text, that implies the length of this word plus the length of this word plus the length of this word plus the length of this word. The total length of all these words and all those words that are there in our text and we are inserting in our trie, that is equal to n. And what is m? And this is the length of our pattern. This is the length of our pattern. This is the length of our pattern, right? So the length of our pattern, as we saw earlier, it is very small. It is m. So what is the space complexity? So to find out the space complexity, you need to find out the number of nodes that your trie can have. So what according to you can be the maximum number of nodes a trie can have? Will it be the number of words in your text? Like in this text there are 5 words, so will the number of nodes be 5? No, we saw in this example itself that if we consider the number of words in our text as the number of nodes in our trie, that will be an underestimation, right? Here we are looking for the worst case space complexity. So let me show you an example. Just suppose you have got a trie like this. I have made this trie out of this text containing all these words, right? So here you can notice that there are no overlapping words, right? Here every word is actually starting from a different letter. And in this, if you calculate, the total number of nodes will be actually equal to the total length of all these words. Like suppose if here the total length is somewhere around 60, so the total number of nodes are also 60, right? Because for beer you have got 4 nodes because the length of that word is 4. And for elephant you have got 8 nodes because the length of the word elephant is 8, right? So in this way, so here I have given you an example of a trie where the total number of nodes is actually equal to the total length of all the words. Or you can say that the total number of nodes in the trie is actually equal to the total length of your text. And what was the length of your text? It was n, right? This is actually the number of nodes. And what is there in a node? So there is a data value, let us not consider it, but there is also an array, right? And the size of that array is 26. Let us also consider this as constant. So basically your total space complexity will be order of 26 into n, right? Into the length of your entire text. As we can see in that example, that is actually the worst case. So here the space complexity is you can consider as order of n because this is a constant. So the space complexity in case of a trie can be very high, right? As you can see in that example where every node is having just one child, right? Here you will see that every node except the root node is having only one child. So the next question comes that how we can improve the space complexity of the trie. So how we can store tries more efficiently? In order to answer that question, let us meet in the next video where we will discuss compressed tries. If you like this video, share it as much as possible. And do subscribe the channel because I'm going to upload many such videos in the upcoming days.